the first lecture of Chapter 8. Chapter 8 is devoted to inverse of a matrix and relationships between linear dependence of vectors, rank of matrices, and invertibility of matrices. So let's talk about the inverse of a matrix right now. We will cover two ways of finding the inverse of a matrix. So first establishing whether the matrix is invertible or not, and then if it is invertible, finding the inverse of a matrix. Theorem, part A, let A be a square matrix, then A is invertible if and only if the determinant of A is different from 0. And part B, in such a case, if we denote by A to minus 1 the matrix with scalars xij, we have the following formula: xij equals -1 to the I plus j power times determinant of aji divided by the determinant of A. Here aji is the matrix that we obtain from A, removing the jth row and the ith column. The proof of this theorem goes back to lecture 7.4, where we had another theorem that was expressing the solution of a system of linear equations in function of the determinant of the matrix A, assuming that the number of unknowns was equal to the number of equations. In fact, this is a corollary of this theorem. Now, there is another way of finding inverses of matrices, and this second way, which is very effective, uses elementary operations. So a quite effective way of finding the inverse of a matrix, of the invertible matrix, is through the use of elementary operations that we introduced in lecture 6.7. That is the concept of elementary operations. So I recall here a few basic facts of elementary operations that we will need to use in order to find this procedure of finding the inverse. If T is a row elementary operation, then the operation applied to a matrix A is the same as a matrix multiplication. So we take A and we multiply on the left by the matrix that we obtain by taking the identity matrix and applying the same elementary operation T. Well, this is the remark that we have done in the chapter 6, in the lectures of chapter 6. Second point is that if A is invertible, there exists a sequence of row elementary operations T1, T2 through, let's say, Tn, such that if we apply successively, starting from T1 up to Tn, these elementary operations to A, we eventually get the identity. Now, to prove this statement, we just use the same techniques that we used to prove the theorem of lecture 6.7, which was a reduction to row echelon form. Well, it follows then that the inverse of the matrix A can be obtained just by applying to the identity matrix the sequence of row elementary operations starting from T1 up to Tn. So let's prove the third statement, this one, using the first two ones. We start from T1, applied T1 applied to A. Now we know that this, by point number 1, is simply T of the T1 of the identity times A. Now if you apply T2 to T1 applied to A, what do we get? So we get T2 applied to this matrix, which corresponds to multiplication on the left by the T2 applied to the identity matrix. So T2 applied to the identity matrix times the matrix T1 A, which is the same as T2 of the identity matrix times T1 of the identity matrix times A. Now if we concentrate to this multiplication, we simply see that this, always because of the point 1, is T2 applied to T1 applied to the identity matrix. So recursively applying this argument, we eventually end up with the following: Tn applied to T2 applied to T1 applied to A, well, is equal to, well, we jump to the end, Tn applied to T2 applied to T1 applied to the identity matrix times A. Now for the point 2, using the point 2, we know that this is equal to identity matrix. Therefore we have here on the left the inverse matrix of A, as stated here in the third point. Well, we've just shown that we need to apply this technique to reduce A to the identity matrix by row elementary operations, while keeping track of all the operations used. And then we apply all of them in the same order to the identity matrix. Let's see this in an example. So we call A the 2 by 2 matrix 1 and -1, and then second row 1, 2. In order to keep track of all the elementary operations we will be applying on A, and simultaneously applying them on the identity matrix, we create the following matrix. It's a block matrix. On the left block we will have the identity matrix, and on the right block we will have A, the matrix A. Now if we apply a row elementary operation to this block matrix, the fact that we get is the same as applying the row elementary operation first on the left block and then on the right block. So this way, focusing on the right block and trying to make it the identity matrix, 2 by 2 identity matrix, we will eventually get, if of course A is invertible, we will eventually on the left block end up with the inverse matrix of A, simply because at each stage we will be applying on the identity matrix the same row elementary operation we will be applying on A. So let's do that. So we operate on the rows of this matrix, trying to reduce the A block to the identity. When finished, the left block will be the inverse matrix of A. Let's first use this real number 1 here in A to kill the number 1 here on the second row, performing the following operation: replace row 2 with row 2 minus row 1. This is what we get. So A is invertible, and we can see it right from here. Next step, we want to reduce this 3 to 1. So we will be dividing by 3 the second row, 1/3 times a second row R2, and we end up with this matrix. Now we are almost there. You see there is just a negative one here, which we can kill by replacing the first row with the sum of the first row with the second row. So next step, R1 plus R2 replacing R1. What we get here is on the right hand side block the identity matrix, and on the left hand side block the inverse of matrix of A. Identity matrix here, so we are done, and here therefore we'll have the inverse matrix of A.